Okay, let's look at the dual of the convolution theorem. Now remember, duality in this context means interchanging time and frequency. So duality means N interchanges with K, or T interchanges with omega, if you want to think physically. That's what I always mean when I say something is the dual of something else. I mean interchange time and frequency. And all these Fourier theorems have dual versions of themselves. So you can get a second Fourier theorem by just taking the dual of the first one. So the dual of the convolution theorem says that a signal times another signal pointwise corresponds to the convolution of their spectra. And because we use unnormalized sinusoids in our definition of the DFT, we get a division by n here. So this is an argument for using a normalized DFT where your sinusoids are divided by square root of n, square root of capital N, because if you do that, you'll get prettier Fourier theorems, and you'll get more symmetric dualities. And so the proof is identical to the convolution theorem. There's nothing new there. J is positive instead of negative. Now, another nice thing to point out here is that this helps us understand windowing. So time domain windowing. So when you, and normally we say, let W equal, first of all, it's in Cn, but really we'll always use Rn. In other words, when we do windowing, we almost always choose a real window. So if you have a frame of data X, and it's usually just a chunk of data out of your signal, you multiply it by your window. And in the window is virtually always a zero phase thing. So it's always symmetric about time zero. Well, not always. Some people like to start it at time zero, but you'll see that I always like to see it centered about time zero because then it doesn't introduce any delay. So it's an even function. It's a real even positive function in just about every case. And that's what we use to window our signal in the time domain. So you take a chunk of data and multiply it by a window, and the window doesn't always go to zero. Like the Hamming window looks like this. It's offset from zero. And so we multiply it times the data. And so now with the dual of the convolution theorem, we can say that what that gives us is the convolution of the spectrum of that frame with the window transform. Times 1 over n, which is just a scale factor. So this multiplication of the time domain, sometimes it's called modulation, but we will call it windowing. And then in the frequency domain, this is smoothing, right? We're smoothing by convolving the spectrum with capital W. And we want the window transform to be approximately a delta function in frequency. Because if it's approximately a delta function, then x convolved with it will be approximately itself. Because the delta function is the identity operator in a convolution. We saw that in the impulse response. If you convolve any signal with delta, you get that signal back. It's like multiplying by 1. And in the frequency domain, it's multiplying by 1 because the transform of delta is 1. Okay? So this shows you that windowing in the time domain corresponds to smoothing in the frequency domain, convolutional smoothing in the frequency domain. So this is extremely important because practical spectrum analysis uses windows. And so you have to learn how to recognize the effect of that window on your spectrum. So everything you see in the frequency domain will be through the lens of that window transform. You'll have some underlying true spectrum that has been convolved with your window transform. And so really understanding that helps you distinguish between what's real in the spectrum analysis and what's an artifact of the processing, what's an artifact of the particular window you chose, the particular window transform that it has. Okay, now a topic related to convolution is correlation.